Oh my God, I have more than one person in this room. I don't remember the last time that happened. What was that, 2 weeks ago? I don't know. Riding a bike uphill here and then forgetting a drink is a bad idea. Also a bad idea. Instead of getting water, getting a Coke with cherry in it. But, you know, baby steps. Welcome. Oh my God, I have 3 of you. Whoa. Exciting.
Do you know if the library is going to be closed from now on?
So,
Do you know if the library is going to be closed from now
I don't have a definitive answer on that, but I know that when I was working in there, he liked to consider it as being something he wanted open like year round. So you're probably good. I don't know if they're gonna shorten hours or anything, because honestly, I've been ignoring everything that says all.college@wnc.edu.
Yeah, because I got an email about the Chromebook that I thought.
Okay.
So I wanted to see if I had to turn it in already or if I could keep using it since I'm doing the KET program. But I just went over there right now because yesterday I saw the hours saying that they're open until 8, but I just went over there right now and it's closed.
Interesting. I do not have a definitive answer for that. That is best asked of people who know more about administration than me. Literally, all I know is math. Everything else I'm completely useless on.
When did you fit it?
Oh,
You know,
a couple days ago.
oh, really? Because I have one too, but I don't get it.
Yeah, it's weird.
Those jerks. Can I just go to sleep? I just want to go to sleep. Am I recording this? Oh yeah, that's recorded. Cool. Me complaining is recorded. Give it to the world.
So since you have one, I was already able to hold on to it.
Oh, really?
That's like it's a minimum process.
Oh,
That's what we will do.
Oh God, sitting. I like sitting. Oh. I don't know why I thought it was a good idea. It's like, you know what? I'm making good time. Let's ride 20 miles an hour up this hill. I had pedal assist on because it has a motor on it, but I still kicked my own butt.
They say the 2 degrees outside, so.
Is it? Huh. I don't like that. I like winter.
That might have been a small.
Hmm. I don't know. All I know is I'm getting an interview for a new job, so I am happy.
Tomorrow.
Huh?
Tomorrow.
I haven't gotten an email about it, but it possibly. I don't know. I sent them my availability for an in-person interview earlier today. And then I'll start sticking people and drawing their blood out. Yeah, land of opportunity.
Where?
There's a plasma donation center over by like Target on the far end of town. So, you know, I'm gonna kick my own butt riding my bike every day. It's only 6 miles from my house. That's not bad on a bike.
What's the time?
15-ish. Yeah, getting ripped off, I know, but yeah, I get paid. And right now, other than this, my pay rate is at 0. So zero.
Did you go to school for that or like? No, they're just willing to pay.
They're actually going to license me. They're going to train me and license me.
Oh, I thought you were licensed, because I was gonna say, I think Renounce might be for people.
Yeah, there's even
They're starting at 18.
there's a place over off of College Parkway about all of maybe 1.5 miles, 2 miles down the road. And their phlebotomist just moved to Texas. And I'm like, I wonder if I could get licensed through one job and then quit. And then go to I don't know if that's too much of a
Now
trick.
you're starting to sound like a real cost employee.
All right.
That's what that's what they do.
I mean, why not? The employees market right now.
It is. It really is.
I was all excited that I have 3 of you in the class. I have nobody online. It's gonna happen. I'm gonna be stubborn and wait a few minutes, but I'm gonna find it funny if that just doesn't happen. So before I start, I know that there was only a couple of people that attended on Thursday, but I know I terrified so many people with what I covered on Thursday because I just kind of gave you all a preview of what is on the high set. So I've bounced around a lot of ideas and I want to get your guys' opinion on this. Right now, I'm thinking that the last 2 classes, instead of a review for everything I've covered, I would do an actual high set practice test and explain everything as I go. And that way you guys will have seen at least a little bit of everything. Is that good? Is that bad? Or do we want to stick to reviewing what we've covered? Whatever.
No, I think the test is.
I think that.
Yeah.
I think I'd like to see that.
I like that idea too. One thing I'm probably going to try to do before then is type out the entire test and rearrange it in an order that doesn't suck. Because honestly, every practice test I've ever seen for the high set is in a jumble. So that's something to keep in mind, is that if you go into the high set, don't expect the easy ones on the front and the hard ones on the back. It's going to be all over the place. So yeah, we'll figure that out. Right now, that's my favorite idea. So I don't want to leave you guys hanging and not show you at least a little bit of everything. So it's the best idea I got. I've never tried it before. You guys are my guinea pigs. And everyone joining right now online is like, wait, what's going on? What's going on? Don't worry about it. Don't worry about it.
Just show up.
Yeah, just make sure you show up in the last week. Make very sure that you show up on time for both of the last 2 classes, because there's going to be no review. We're just jumping right into it. And we're going to do 50-ish math problems that you've never seen before. Okay, you might have seen like 20 of them, but still. It's gonna be rough. So my high recommendation for everybody is after this class, because I know a lot of people aren't using Essential Ed. After the class, particularly after that last week when I cover a bunch of stuff that you're not going to see before then, jump on essentialed.com, do some of those lessons. You know, I don't know exactly if you can jump on them out of order or what, but that's an idea. And I'm also going to email everybody a playlist I found on YouTube where it covers, it's literally somebody just grabbing all the Khan Academy videos that cover every subject that would be on a GED or a high set, and they put them all in one giant horrible playlist. There's over 200 videos, but I think the longest one was 7 minutes and the shortest one was like 1.5 minutes. So I think on average, all the videos were like 4 minutes long, so it's not bad.
Do you happen to know if math work on the Essential Ed is also
The stuff that's on that,
on the KET?
on the what?
On the KET.
Oh, the KET fast forward thing.
Yeah.
It's like a more simplified version of the same thing as far as I could tell. So it covers a lot of the basics, a lot of it. So everything that I would cover, I don't know if it goes as far in depth as the fast forward would be, but everything on Essential Ed has like a 2 or 3 minute lesson anyway. So, I mean, if you still have a login for both, it would probably be good to like look at both at the same time, kind of treat them as like they're separate lessons, but the same thing, you know? Because I think that would actually benefit most people. All right, so we got a bunch of people. We even got one sitting in, which is great. I'm not greedy. I'm not trying to randomly add people to my class that don't count as students. I'm not greedy at all. I don't know what you're talking about. But tonight we are going to be covering stuff. We're going to be reviewing the basic stuff on scientific notation that we did last time. Radicals and roots is the reasonable next step. That's, you know, we've already done exponents. So, you know, with scientific notation, that's exponents. So radicals and roots is literally same thing the other way around with a little squiggly bar. What?
That one's straight too.
Oh, yeah, I like that one. I like that one a lot. I was like, this is inappropriate. I shouldn't put this on my slides. I'm like, all right, fire me. I don't care. And then after that measurement, yeah, sure, I could paint your ceiling. Michelangelo scoffs to himself. Gonna paint a bunch of dudes with their dicks out, though. Actually, if you look at the history of the Sistine Chapel, Michelangelo had a lot of issues with them, and he put all kinds of hidden imagery in that thing. There's a reason it's still considered one of the greatest works of art that we've ever done. Also, who would paint a ceiling? My God, that place is huge. Like, God, that would suck. Paint your ceiling with an intricate painting. No, maybe with like a squeegee or something. I don't know. Okay, so scientific notation. It's been, you know, 5 days since anybody's looked at this. So let's look at some basics on it. So scientific notation is always written in 2 parts. You got just the digits that are important, and the decimal point is always placed after the first digit. So if you see anything in scientific notation where that's not the case, then it's not in the correct form and it needs to be adjusted before you're like done. And then it's followed by times 10 to a power. And depending on what power that is, you're multiplying it by however many tens or dividing it by however many tens. And that just kind of shifts the decimal around. It makes it either a bigger number if you have a large power or a small number if it's a negative power. So we're going to be looking at a few of each of those. I will give you guys the heads up. I'm not going to be doing as many review questions as I can in the next couple of weeks. This is what, week 6? I'm just saying that off the top of my head. I think it's week 6. I don't know. I don't have a memory. I don't honestly know how I have this job. I'm just kind of rambling. I'm a math teacher who has no memory. How does that work? You know. that part of my brain works, the rest of it don't. Yeah, so we're in week 6, which means that for straight up lessons, we have a grand total of what? 6, 7, 8, so 3 weeks left. So we have 6 more classes left. The last 2 classes are going to be a review and a preview in the form of a practice high set test that I will be working out and explaining as I go. So that means we have a grand total of 4 more lessons. And with those 4 more lessons, I'm going to try to cram as many concepts as I can. So if you can, make sure you're attending in the next few weeks, because earlier today I was like, yeah, I think I can fit all of algebra in 4 hours. Yeah, I could probably do that. I don't know. I'm going to pull it off. We're going to throw everything I can at you and we're going to see what sticks. It's going to be fun. It's going to be fun. Okay, so as I discussed last time, these are the strict rules of how you move things around in scientific notation. If it helps you, awesome. It does not help me at all. This is not how my brain is wired. These are just strict directions that you would find in any textbook explaining to you how to do scientific notation. To figure out which power of 10 you have, if the power number on the 10 power is greater than, when the number is 10 or greater, what? That's a typo. I'm like, wait a minute, that can't work that way. There we go, I fixed it. When the number is 1 or greater, because why would I ignore every power between 1 and 9? So if the power on the 10 is essentially, it's a positive number, the decimal point is going to have to move to the left, because the decimal point's at the end of your number. So if you're going to make this thing smaller, that decimal point's going to have to travel to the left. And that'll make the power of 10 positive. If you're converting backwards out of that, if you're converting back to decimal, you would have to move it to the right to kind of undo that. And then if the number is smaller than 1, meaning a negative number, the decimal point has to move to the right. So the power of 10 is negative. To convert back to decimal, you go the other way around, so it goes left. Those 2 separate right and lefts kind of turn into a giant jumble in my head, and I can't remember that. I can't. So I have to use my reasoning skills in order to do scientific notation every time I do it. So personally, I would look at this first example where it's point, what is that, 10 zeros, 436, and converting that to scientific notation. The first thing I think is that's a really tiny number. And since that's a really tiny number, if I'm converting it to standard scientific notation, it's going to be a negative power on the 10. So at that point, you would count how many places the decimal point has to move to get from where it is. And I'm going to actually, since I don't have that written out, I'm going to write it on my notes here, and I'll switch over to that in a second. So if I was converting this to scientific, what you would do, the easiest way to do it that I've ever seen before, is literally put your pen at that decimal point right there and just start moving it. Out of the definition of scientific notation, where does the decimal have to be? Well, it has to be after the first important digit, right? First one's going to be 4. So that decimal has to travel over here. So what we're going to do is we're going to put our pen at that decimal and we're going to move it. And we're going to count as we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to get to that point, right? So you would look at this and say, okay, we have 4.36, and then it's times 10 to a power. What power is that? Well, it'd have to be an 11 because that's how many times we moved that decimal point. And then since this is a very tiny number, the power is going to be negative on that. And if you remember, the reason that the power is negative is because if I had, say, as an example, 1 times 10 to the negative 1, by the rules of exponents, a negative exponent would have to jump to the other side of a fraction. So that would become 1 times 1 over 10 to the first power. So 1/10 of 1 would be 0.1. So essentially the decimal that's right here just moved over by 1. So that's what's happening when you have a negative exponent, is you're actually dividing this number by 10 that many times. Okay. Now, if we look at the second part of that example, if we're converting them back, so in this case, we have 4.2 times 10 to the negative 7th. And we'd be converting that to decimal. Converting that to decimal notation. So since the exponent on the 10 is negative, you're looking for a small number, as we covered. And since the exponent is a 7, you'll be moving the decimal point 7 places to the left. So again, working that out, kind of have to do it a little bit of a different way, but I would have the 4.2. I would just write it as 42 for now. I kind of skipped the decimal, but I will put my pen where it was, right? And we say, okay, what's our power? -7. Okay, so this is a small number. So to make it a small number, the decimal would have to be over here. And it's moving 7 times. 1, 2, 3, 4, 5, 6, 7. So that's where the decimal point's actually going to be. And everywhere else, you're just going to fill in zeros, kind of like how we got rid of the zeros on this one. We're just going to fill them in. Okay, so we have 6 zeros. And then if you want to rewrite it, normally it has to be 0 point something. If you want to split hairs about the definition there, you can't have a point, a decimal point floating in nothing. You have to have something point something else. So that's why we put the 0 there. Just an extra 0, has nothing to do with how many times we move. But that's how you would convert out of scientific notation. I kind of move this guy up here, so it's still going to be visible when I do the first example. So we only have a couple of examples on this one, 2 converting to scientific notation, 2 converting away from scientific notation, and 2 where we're fixing it. After that, we'll look at the new stuff, which the new stuff is still going to be dealing with scientific notation, but it's going to be operations with it. So adding, subtracting, multiplying, dividing. And kind of like fractions, adding and subtracting scientific notation is more of a headache than multiplying and dividing. Multiplying, dividing, easy. Adding and subtracting, it's kind of weird. You'll have to bear with me for a few minutes on that one. Is there going to be any adding and subtracting on the high set? Don't know. Don't know, but I figured we'd cover it. I guess we'll find out when we do a practice test. Remember, the practice test isn't going to be all encompassing, but it'll still give us a decent idea of what type of things you guys are going to run into. I'm just going to go ahead and copy over the first 4 problems because those are going to be really quick and really easy. And I don't know if I'm going to fit 5 and 6 onto the same page. So we're going to worry about that later. Look at how much space I gave myself for 4 problems. I'm probably not going to need all that space. Because first 2, we're going to convert them to scientific notation. Next 2, we're going to convert away from scientific notation. So this first one, first thing you're going to do is identify where the decimal point is. If you just have a very large integer, that decimal point is always at the end, right? So you would put your pen there and you'd start moving it until you're after the first digit that matters. First digit that matters here is going to be 7, right? So we're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we've moved 10 places. Cool. So we're going to have 7 point. Now, which part of these matter? Everything up to the point where it's nothing but zeros afterwards. So 7.031. This is the part that matters. I could use more complicated terms, but honestly, that's going to be the best way to make sense of it. If you feel like going on YouTube later and looking up a lesson on significant figures, go for it. I don't recommend it. Cool. So our power was 10 because we moved over 10 places. And that's it. That's all we need for converting to scientific notation. That's it. Now for number 2, that decimal point is going to be moving this direction, right? So this is a small number. And since it's a small number, since that decimal point's moving to the right, our power is going to be negative. So let's worry about that more in a minute. Right now, we're going to set it up kind of like we did on this one. We're going to put our pen at the decimal point, and we're going to move over 3 times until we're after that first digit. So we're going to have 4.1002. Even though it has a bunch of zeros in the middle of it, that 2 makes those place values matter. We can't magically make those places go away unless you're rounding to a different point, at which point that kind of makes scientific notation useless. So what we're going to do, we're going to put times 10, and our power is however many times we moved over. 1, 2, 3, and we move to the right. We make this a small number, so it's a negative. Cool. Now, in the same vein, these are already in scientific notation, but we're going to get them out of scientific notation. So, kind of like I did on the example, what I usually do personally, you could do it a slightly different way if it makes more sense to you. I'm fine with that. But to get out of scientific notation, just like the example, I usually write out the numbers without the decimal point for now, because that's not where it's going to be. But I am going to put my pen there. And I'm going to move that over 9 times. Now, since this is a 9th power, that means this guy's going to be huge, right? We're multiplying by 10 9 times. So this is a big number, kind of like we had up here. This giant, horrible thing with that many zeros was a big number. So we had 10 times we multiplied by 10 for this guy. So we're just going to move over 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is incredibly dark because I am an idiot and I just held my pen against the page for a really long time. So it just kept spilling ink on there. Okay, so every time we've moved, we're gonna have to fill in zeros, kind of like on this one. We have nothing there, but we know our decimal is right here. So we have to have our zeros in here. 1, 2, 3, 4, 5, 6 zeros we ended up with. Makes sense, right? We had a grand total of 3 digits after the decimal point here. So if I'm moving it over 9 times, how many zeros am I going to have? 6 more. Okay. So it might be a good idea to rewrite it because usually you have a giant mess of stuff. So we have a very large number. What number is this? I don't know. I could do my commas every 3 if it makes you feel good. You know, okay, all right. So we actually ended up being at we ended up with 1,421,000,000. And that's why we use scientific notation, because if you had to do a problem with these numbers, like if I decided I was going to take something like this and I was going to divide and multiply by a bunch of things that look like that, that's going to be ugly and you're going to be there for a while. So scientific notation is a useful way to get around that. Now, you might ask, when am I going to use this? Honestly, probably on the test. That's probably it. You're not going to run into this too often until you go, unless you decide to continue on with your education and do maybe some physics courses, chemistry, that sort of thing. Chemistry, you're dealing with insanely tiny little things. So you'd be dealing with negative powers a little bit more often. But generally, if you go into something like that, that's when you'll see these. Same thing's happening with this one. We're going to convert it out of scientific notation. So it's a -4 power. So the decimal point is actually going to move to the left because that'll make sure that this guy is a small number, right? So we put our decimal right there. We put our pen there and we move it over 1, 2, 3, 4 times. Fill in our zeros. Then usually rewrite because that's usually a mess. And again, I put the 0 on the front of the decimal place because we can, because it's a good idea, because it's pretty. Because a random decimal doesn't work out too well. How important that is that? Well, it depends on what you're doing and who you're handing it to afterwards. That's like 90% of everything in education. How do I do this? Well, it depends on who it is you're handing it to afterwards. That kind of works for the job market as well. Okay, and then we have 2 more on our review. We're fixing scientific notation. So we have number 5 and number 6, and you can see that these guys are not in proper scientific notation. We get the times 10 to a power fine, but the decimal is not after our first digit. You know, they each have some different weird stuff going on with them. So we're going to fix them. Now, when is this particularly useful? Usually when you're doing math with scientific notation, hint, hint, like the rest of this lesson, hint, hint, you end up working it out, getting an answer, and it's usually not in scientific notation properly unless you are very lucky. It's also being able to understand shifting that decimal around and having it still in scientific notation is actually going to be part of the method of adding and subtracting, which is going to be weird, which I've never really done on paper, so you'll have to bear with me for that particular part of the lesson because it's going to be weird. So each of these we're going to fix. What does this need to be? Well, this needs to be 2.061, right? Times 10 to a power. But what is that power? Well, this is already a very large number, right? And that decimal is going to have to move to the left 2 more times. Since it's moving to the left, you can actually see it as kind of adding to that 6. I kind of write it that way. And then you can fix it a little bit to now be, this is now times 10 to the 8th. If that does not work for you, like it often does not work for me, you can do that little weird dance in your head I do a weird dance in my head of how to fix this. I think, okay, this is a really big number. So this is going to move, if I got it out of decimal, it would move to the right 6 times, right? So if I put it back in decimal, it would add 2 to that power, because it would have to move over 2 more times. That's personally how I structure it in my head.
You know, you have to move it 2 times.
The 2 more times thing, because that decimal started off right here and it needs to be after the first digit. It has to be like this to be in proper scientific notation. So you know it's going to have to move 2 more times. The question is that going to add 2 to this power or subtract 2 to this power? You know, so that's why I kind of do this in my head. I think, oh, well, this thing's gonna, if I pulled it out of that decimal notation, it would move over 6 times in this direction. So if I had to put it in scientific notation to put it back, it actually, this decimal would push kind of 2 more times in that direction. So I'd have that 6, and then it's moving the other 2, so I end up with 8. Same sort of thing happens over here. This thing, not a good number, right? It actually needs to, this decimal needs to move over here. Like that. We have to have a power times 10 to a power. But the power, little trickier, right? So it's actually happening, since this one's moving to the right to be in scientific notation properly. Since it's moving to the right, we're subtracting 2. So this is happening when it's moving to the left. This is happening when it's moving to the right. So you can rewrite it a little bit. It's now going to be 3.12 times 10 to the negative 7th. Can I visualize it the same way that I kind of told you I visualized it in my head before? Absolutely. If I have 0.0312, and this is times 10 to the negative 5, that means that this guy had to go over here to convert out of decimal, and it would have to move 5 times. So if it was moving that way plus another 2, I would have that 5 and then another 2. I know I kind of have that plus there, but you can think of both of these as being in negatives. So this is kind of a negative 5, this is negative 5, and another negative 2 on top. So it's kind of stacking. That might jumble you more than anything else. You can just do move to the left, plus, move to the right, negative. If it's going to end up in scientific notation. If it's coming out of scientific notation, it's exactly the opposite, which is weird. Okay. That's the end of our review. Are we ready to do math with these numbers? Yeah. So, as I said before, adding and subtracting with scientific notation is notably more difficult than multiplying and dividing. So look at the way that scientific notation is structured. By using the times 10 to a power notation, we've reframed our numbers to different positions than where we started, right? So you could think that if I have 1 times 10 to a 50 plus 1 times 10 to a 20, it's not going to be as easy as adding 1 and 1, right? Because they're in completely different place values. So there's a couple of different methods of adding and subtracting with numbers in scientific notation. This is one method. This is not the way we're going to do it, but in a pinch, it would work. One way to convert each number is to convert each number out of scientific notation. So you just switch it back to a decimal, add the numbers or subtract them, whatever it is you're doing, and then convert it back into scientific notation afterwards. That works, but if they give you a question where it's times 10 to a 50, you're gonna be sitting there all day drawing zeros on your paper. And you're also gonna lose your place because I would 100% lose my place. So that's one method. If you do it with smaller powers, it can definitely work in a pinch. The other method is kind of backwards from the last two problems we did. Whereas we fixed the scientific notation on the last two problems, what you actually can do to add and subtract them is to kind of break the scientific notation. Kind of like adding fractions. If you're adding two fractions, you have to have a common denominator, right? That's the only way it works. Otherwise, they just don't go together. So you kind of have to have them in the same terms. So what you do is you convert one of them to have the same times 10 to a power as the other one. And then you could just add the decimal parts. It's still going to have the same power, so you could just fix it later. So if you look at the example here is adding 3.5 times 10 to the fourth with a 2.45 times 10 to the seventh. So you can think of that, times 10 to the fourth, times 10 to the seventh, those are going to have completely different place values, right? Going to be completely in different spots. So what you do, and with the ones that I kind of worked out on my own, I kind of found that it usually works out the best to convert the larger one, so the higher power, to that of the smaller one. So you would take the one that has the higher power, in this case, it's 2.45 times 10 to the seventh. And you would say, okay, if I'm going to add these two numbers together, they're both going to have the same power on that 10. So in order to do that, we take the bigger one and we shift that decimal point a couple of places so they both have times 10 to the fourth. Once they're at that point, you can then just add the numbers. Now, I completely understand that that explanation is so confusing. So confusing. So I will work out both of these problems on the example as part of the notes. This also works with the smaller numbers. So it worked fine with higher powers. It's going to work fine with negative powers. In this example, we again have to reframe our exponents to the same number. So we convert the number with the larger exponent to have the same power as the smaller exponent. So the one with the larger number, you got to keep in mind, -6 is a larger number than -8, right? They're higher, it's higher on the number line. So you would take that -6 one and you'd move it over a couple. So then it's at times 10 to the -8. So you can see the 2.36 here. That period has to shift over twice to get to the times 10 to the -8. So kind of the opposite of what we just did. So we end up with a 236. Then both of our numbers, this guy and this guy, are in the same notation. They're at times 10 to the -8. So then you can just do subtraction. You got that, you subtract that, and you end up with a different number with that same power, and then you have to fix it. The decimal has to move over again, and you end up with times 10 to the -6. Have I properly lost everyone? Yeah? Yeah, cool. I expected that. These ones are weird. They're strange. But it makes a heck of a lot more sense to do addition and subtraction before we do multiplication and division, right? So I'm going to go ahead and switch over. I'll show you both of them. Now, as part of this example, let's think about these as decimals, right? If I quickly converted these out of decimals, this would be 35,000, and this one would be 24,500,000. So you can see that if I had to add these two numbers together, it's not going to be as easy as adding these two guys, just the decimal parts together, because you have this problem happening actually. So the tricky part is how the heck are we going to do that in scientific notation, right? That's strange, it's weird. So what you do is you would look at, and I'm just rewriting the problem right here. You would look at the one that has the higher power. And we're going to say, okay, this is times 10 to the 7th. What we want to do is we want to make this the same power as this. What would this number look like if it only moved over by 4? Well, look at our decimal one, right? Look at our decimal one. Where's the decimal here? Right here. If I move that over 4, instead of 7, what would it look like? 1, 2, 3, 4. We'd have 2450. That's exactly what we do in order to fix this number. Let's look back at this one. If this decimal is moving to the right, it's going to have to move to the right 1, 2, 3 times to get that down. That's going to end up being subtraction. So what I've kind of done here is I've rewritten it and I've just kind of shifted it over 3. So our times 10 to a power is also going down by 3. This is now 2450.0, whatever, times 10 to the 4th. Oh, well, if they're both times 10 to the 4th, with these powers being the same, they're now both at the same place value, which means we can add these two numbers together. We would actually have the 3.5 and the 2450 combining times 10 to the 4th. So what does that look like? Well, it's easy. 2450 plus 3.5. What's 2450 plus 3? 2453.5. We just happen to get lucky on this one because there's just a 0 in that spot. Normally, you just have to add them. Times 10 to the 4th. Okay. So you're kind of done, but it's not in proper scientific notation. So what has to happen? That decimal has to move back. So again, if I'm moving this guy to the left, and I've just moved it 3 times, if I'm moving it to the left, I'm adding that 3. I'd really like to be able to have both of those on the same screen. It's not going to work out nicely. Kind of, yeah. So if I move this guy to the left, I added 2. So if I'm taking this same situation, I'm moving this to the left 3 times, I'm adding 3. So this is now 2.4535 times 10 to the 7th. If I could make this work a little better. I'm staring at it, trying to make this work better. I'm thinking I want to revise my idea that it's better to go with the larger one to the smaller one. I think it's probably better the other way around. That's a crazy idea. Let's try it. We're going to try it with the other example that we had. Same numbers. I'm going to change it up a little bit in terms of how I do it. Here's my current crazy idea. What if I ignored what I found on how to do this and I went the other way around? What if instead of converting the larger one to the smaller one, I did the smaller one to the larger one? Now, in this particular case, that guy's the smaller number, right? Because it's a -8 versus a -6. So what if I converted this guy to look like that one? If I had that decimal here and I was pulling it 2 back, then that would, it just moved to the left, right? If we move it to the left, we add. I actually think this is working out easier. I like this. We're going to do this from now on. It's the easier way. We're going to convert the smaller one to the larger power. But Ben, why did you just randomly change your idea after writing this down in a slide? Well, everything I ever found on the internet on adding and subtracting scientific notation said convert from the larger power to the smaller power. I think their idea was that this ends up being a even smaller number. Well, what happened on the last problem? I took the times 10 to the 7th, I turned it into a 4, and then we had to end up doing another step to convert it back to 7. So maybe it's an idea to stay in that 7. Maybe it would have worked out better. So that's what we're trying right now. This is literally what mathematicians do. We wing it and we see if it works. If it works, we write it down. If it doesn't work, we erase it and never talk about it again. That's exactly how math works. So at this point, we still have this minus that. All we have to do at this point is figure out what 2.36 minus that 0.0452 is. And that answer is going to be times 10 to the -6. There's still the chance that you could end up having to fix notation by doing this way, but I have the feeling it's going to happen less often. So I like this way better. So we're doing that subtraction. We end up with 2.3148 times 10 to the -6. I don't have to fix it because I have 1 digit point the rest of my digits. So it actually worked out a little better. So what I got over here, it is what I got over here. Okay. So that actually got us a few steps less work. Yeah, we're gonna keep this idea. Convert the smaller power to the larger power when you're adding and subtracting scientific notation, period. That is now set in stone. I have decreed it. That will work. It will work every time. And if it doesn't work every time, well, I'll fix it. But We got 4 examples, so we got time to figure this out. I might only do a few of these, depends on whether or not we're freaking out. But let's give it another shot. We have 1.26 times 10 to the 6th plus 2.4 times 10 to the 4th. And let's try my made up method again, because I like it. So if I'm adding these two, what we're going to do is we're going to convert the smaller power to the larger power. So this one with the times 10 to the 4th is obviously the smaller power than the 6. So what we're going to do is we're going to convert this to times 10 to the 6th. What we're going to do is that's going to have to add 2. And if I'm adding 2, that means that decimal moves to the left. So instead of 2.4, that decimal is going to move 2 places to the left. So now what do I have? I have 1.26 times 10 to the 6th plus 0.024 times 10 to the 6th. Since our powers are now the same, we can now just add the numbers they're attached to together. So we end up with 1.284 times 10 to the 6th. And again, I don't have to fix the notation, so that did work out better in this case too. Cool, cool. This is working. I like it. I like it. I'm now disagreeing with everything I found online. We're doing better math here than they did previously. We are fixing math. See, this is why I say I should write a math book. Because that's easier. I don't want to make this harder. I don't want to make this harder at all. That takes too long. That's too many steps. Let's make it easier. Let's do another. We have 4.72 times 10 to the 4th minus 3.64 times 10 to the 7th. Now, the first thing I notice is that this being times 10 to the 4th and this being 10 times 10 to the 7th, this is going to be a larger number. So we are subtracting a large number from a smaller number. Chances are our answer is going to be negative, right? That's what I'm getting from that. So we're going to do our same thing. We're going to convert the smaller power to the larger power. That's going to be this guy, right? So this guy, we're going to have the 472. We're going to have times 10 to the power, but we have to add 3 to that power. And in order to add 3, we have to go to the left. So that decimal is going to go 1, 2, 3 places. We end up with 0.00472 times 10 to the 7th minus 3.64 times 10 to the 7th. So we've ignored this guy until now. They're framed correctly. They have the same power. So now we can just do the subtraction with these guys. 0.00472 minus 3.64. We get negative 3.6. Oop, that fixed it. That doesn't look terrible. Negative 3.63528. And that is still going to have the same scientific notation, times 10 to the 7th. So the only difference with this problem versus the other ones is that it ended up having a negative number, but that's fine. It's just a negative number. Not too worried about that being negative. Okay, all right. Probably need to do another two to, wrap our heads around this, right? I got two more examples. Gonna give you a second. What's with me and making a trick question? Last one's gonna be funky. It's gonna be short, but it's gonna be weird. Okay. It's number 3. We have 2.0 times 10 to the 5th plus 2.0 times 10 to the 3rd. Why the basic numbers? Because really, it's the concept we're after. So we're going to do the same thing. We're going to convert the smaller power to the larger power. So this 3 needs 2 more. So we're going to add 2 to it, which means that decimal is going to have to move to the left 2, right? So if I'm moving 2 to the left on this guy, what do I have? I would actually have 0.02 times 10 to the 5th. We're kind of adding 2 that way. There we go. But Ben, what happened to that 0? 0.02 is the same as 0.020, so we don't really need to write it. If you feel better writing it, that's fine. We're cool with that. Doesn't matter either way. Well, now they're both in the power of 5. So I could just add this to that. What's 2 plus 0.02? 2.02. Same power, and we're good. So it's getting a little bit quicker. You can see that. One more. Random quick trick question. Ones everywhere. Look at the ones. You will never see a problem like this on your own because there is literally no point in writing this in scientific notation. None. This is a terrible scientific notation problem. The answer is 9.9, whatever. So again, we are going to convert the smaller number to have the same power as the larger number. How do I go from a -1 to a +1? We have to add 2. Did I intentionally make all of these problems dealing with adding 2? No, that just kind of happened that way. So I'm gonna write it. Let's keep the negative as its own thing. That it is this minus that. So we're just going to remember we're subtracting. So if I have this thing and I'm adding 2, again, adding 2 means we're going to go to the left twice, right? So the decimal's right here. That's going to go over 1, 2 times right there. So we would have 0.01 times 10 to the 1. Well, this is still here, right? So I'm just going to rewrite that here. So we have 1 times 10 to the 1 minus 0.01 times 10 to the 1. Okay. What's $1 minus a penny? 99 cents, right? That's basically what's happening here. This is a solid 1 minus 0.01. So what do we have? 0.99 times 10 to the 1. Well, uh-oh, this is not in proper scientific notation, right? Because we have to have one digit point the rest of the digits. That decimal has to be right there, right? So we have to fix it. We do have to fix it. How do I fix it? I would have to take that decimal and I would have to move it to the right by 1. Well, we've been moving to the left and adding to the power. So if I move to the right, it's going to subtract from the power, right? We would end up with 9.9 times 10 to what? I just moved over 1. I'd be subtracting 1. What the hell? 1 minus 1. The power on that 10 is 0. Uh-oh, what the heck do we do? That's weird. The reason it's weird is because, like I said, you're never going to have to do a problem like this on your own because there would be no point in doing this problem in scientific notation. You know why? Because anything to the 0 power is 1. This is 9.9 times 1. Anything times 1 is itself. It's just 9.9. There is no way to write that in scientific notation because there is no movement on the decimal. You can kind of see that happening because this up here, our original problem, 1 times 10 to the first minus 1 times 10 to the negative first. 1 times 10 to the first, that's just 10. 1 times 10 to the negative first. What's 10 to the negative first? 1/10. So this is 10 minus a 10th, 9.9. There would be no point in doing this with scientific notation other than torturing you guys. I'm sorry. Cool. Are we okay with not doing these anymore? Yeah. Yeah. So again, I want to say I am not sure if something like this would be on the high set because I am mostly used to multiplying and dividing with scientific notation. I am not used to adding or subtracting in scientific notation. If I've gone through and I've gotten a degree without having done this before, I don't know how important it is. I don't know how important this is. Now, let's go back to our slides and let's look at something else. We've done adding and subtraction. How about multiplying? Does that sound more terrifying or less terrifying? Everybody wants to say more, but it's so much easier. And it's actually annoying how much easier it is to multiply and divide scientific notation versus what we just did. Because think about it. What is 2.3 times 10 to the 5th? It's a number, right? We've already established that even though we have that notation, it is a number. But the way we're doing it is we're doing it as something times something else, right? Well, when we multiply that by another one, we have something times something else times something else. Well, remember the whole, like the commutative property of multiplication? I had to think about it and I wrote it on the slide, whatever. If you remember the commutative property of multiplication, which again, do you really need to remember it? But it's useful. When I said it would be useful later, this is what I was talking about. Because what we can do is, since this is just a jumble of stuff with multiplication symbols in between them, we can rearrange it. We can rearrange it and it'll make our lives so much easier because you can look at it and say, oh, well, if it's just this times this times this times this, I'd rather multiply the two that fit together nicely and then the other two that fit together nicely. It's going to make your life easier, right? So look at that second line there, 2.3 times 9.2. If everything is multiplied together, you can rearrange it. which things would I prefer to multiply together? The things with the powers on 10, I would like to cram those together. And then the other stuff, I'll cram those together. Okay. So that's what you do. You literally just multiply the number parts together and then the times 10 to a power parts together. And that's it. Now you might have to fix your notation. Like honestly, 50% of the time you have to fix your notation, but that's it. Okay. Now, we also have dividing. And dividing takes advantage of the same idea. I am an embodiment of that meme. I just want you all to know that. I know what I have to do, but I don't. So it follows the exact same idea. I could just divide the parts that work best together times 10 to the parts that work together, and it ends up being an easier problem. So because both of those concepts are so closely related, I figured that I would just put them together on one example page, and we'll do a couple on each. Also, this is the greatest stupid meme I found as part of a Facebook group of Star Trek things ever. Mr. Data set a course for Flavortown. It is the dumbest thing I've seen in a very long time. I have now given it to all of you. That is my gift. I am sorry. I am truly sorry for what I've given to you. Okay, so I'm going to write down this problem, and I'm going to decide that my handwriting is awful and rewrite part of it. Okay. All right. So we love these problems. You know why we love these problems? We love these problems because all I got to worry about right now is multiplying those two numbers together. No reframing required, no moving stuff around. Multiply those two numbers together, that's it. 5.34 times 2.54. I get 13.5636. Okay. So that's part of it, but we're also going to end up with the scientific notation part, right? Well, think back to when we were doing exponents. When you're multiplying two items that have exponents together and they have the same base, what do we do with the power? I have 10 to the fourth times 10 to the negative 5. So I have 4 of them, and then I have negative 5 of them, and those are cramming together. So what happens? Well, we can just add the powers. We have 10 to the 4 and 10 to the negative 5. So we're just going to have the 4 and the negative 5 combining. That's it. We end up with 13.5636 times 10 to the negative 1. But this isn't fitting our notation, right? It's not fitting our notation because that decimal needs to move. It has to be 1 digit point the rest of our digits. So that decimal needs to move 1 to the left. And remember, if we're moving it to the left, you're going to add that to the power. Well, the same thing happens on this guy that happened on the last example. That was entirely unintentional by me, for the record. But you would end up with times 10 to the 0. If you end up with times 10 to the 0, you can just remember, I don't need that part. So we actually ended up with something that didn't need scientific notation. So does that look easier than the other ones? Well, that's not good. It is easier than the other ones. You know why? Because I had to move that decimal to fix my answer. I had my answer right here. On step one, that was it. That was really it. I multiply these two numbers together and put them there. I add these two numbers together and put it there. Everything else on the page is just fixing my answer to not look stupid. So that's why I did stress that the fixing scientific notation was a very helpful concept, because that's the rest of the problem. We basically had an answer on the first step. Don't worry, we got 3 more. Actually, we have 1 more based on each of these because I only have 2 examples for each. And I'm going to change their order because I don't know why I would have done that. Okay. Keep this up here for a second for anybody that's writing still. Good, everybody good? Yeah. All right, let's look at another one. For another one, we have 4.5 times 10 to the negative 14th multiplied by 5.2 times 10 to the 3rd. So if you look at what it is we're working with, times 10 to the negative 14th, this is a really teensy little number, right? That's what that guy is. It's just a really tiny little number. Times 10 to the 3rd, that's like 5,000, right? So we're gonna have 5,000 times this tiny little number. But just like the last problem, what are we going to do? We're going to multiply just the numbers together. So we have 4.5 times 5.2. We end up with 23.4. Okay. Times 10 to what? Well, if we're multiplying these two numbers together, the times 10 to the negative 14th and the times 10 to the 3rd, just add the powers. What's negative 14 plus 3? Negative 11. We're just adding 3 to it. So normally you'd like to be done, but again, you got to fix your notation like most of these. So that decimal point is going to have to move over once. And if it moves over once to the left, that means we're going to have to add 1 to that power. So we're actually going to have 2.34 times 10 to the negative 10th. And that's how you know I have a black cat. It's this random hair that followed me a mile. So how do we feel about?
When was that 1 plus 1?
Because this decimal had to move to the left. And if it moves to the left, you have to add 1 to the power. If it moves to the right, then you subtract the power. Going back to a couple pages back, but nope, even further back. Yeah. So remember here, this one moved 2 to the left, so we added 2. This one moved 2 to the right, so we subtracted 2. So if you remember those 2 pieces of information, you should be able to fix scientific notation. And if you still hate your life doing that, just convert it to a decimal and then convert it back. Because I will tell you right now, worst case scenario, you're in a test, you're freaking out. Oh God, I don't know how to do these. I don't know how to do these. So let's just use this one as an example. Do I recommend doing this? No. But if you're in a pinch, if you're in a test and you've been working at it for a couple hours and your brain is goo and you're like, and you turn the page and you see scientific notation, you're like, oh God, I hated this. I don't want to deal with this. This is awful. I don't want to multiply these. Well, convert them back to decimal. This is times 10 to the fourth. So that decimal would have to move 4 places. So you would have that number. This is times 10 to the negative 5. So it would have to move 5 places to the left. Oops, there's a 5 in there. There we go. That looks awful, whatever. Okay. Just multiply those two numbers together. You get 53,400. Can I frame this nicely? Have I run out of places that I can cram that? I'm like shoving it up against the camera to make that work. 53,400 times 0.12340, 254. Hey, look, we got that. So worst case scenario, you're in a test, you're freaking out. You can usually get away with that. When can you not get away with that? Well, if you have gigantic numbers like this, that decimal point would have to move over 14 times. So you'd actually have to do 0.13 zeros and a 45. I don't know if your calculator can pull that off. That's a lot of digits. So that's why I said I don't necessarily recommend it, but in a pinch, if your calculator can handle it, it'll work. So now that we've done multiplication, I have a few examples of division for you, and this is going to be a perfect example of why I would not want to do it that way. I have 1.5 times 10 to the 40th divided by 3.2 times 10 to the negative 59th. And kind of like when we're doing more complex stuff with like exponents and stuff, usually a problem like this you would see as a fraction. So I'm just going to rewrite this that way. Fractions and division, again, are the same thing. So we basically have that, right? So what you want to do is you want to actually work out this part on its own and this part on its own. So the first thing you do is you go to your calculator and you say, that thing divided by that thing. Okay, 1.5 divided by 3.2, we get, okay, that's a weird number, right? That doesn't compute all that much, but hey, whatever. 0.46875. Okay, cool. Now, kind of like the last thing we did. When we multiply these two powers together, we add them, right? So remember with exponents, if I'm dividing them, they have the same base, and I'm dividing these numbers, you're going to subtract, right? If multiplying adds, then dividing subtracts, right? You can kind of think of it that way. Well, what ends up happening is you end up with 40 minus a negative 59. You have to be careful of the sign. Bless you.
Thank you.
You have to be careful of your signs, because if I'm doing this power minus that one, bless you again, you got to say that, otherwise your soul jumps out. I think that's where the superstition comes out. I think, you know, your soul's jumping out, demons coming out. I don't know. Probably not the demons, because you'd want them out. I don't know. I'm not up to date on my superstition stuff. You ever like You ever be sitting around somebody like coughs horribly and you just kind of wish you had something like bless you to say? Why don't we have something for that situation? You just kind of like sit there quietly for a second. You're like, you okay? You all right? You turn it into a discussion. We need to have just like a thing you say, like, right? That would be so much easier. I don't know. I mean, obviously, I am an awkward nerd. So these are the things that I've put my time into is how do you have a conversation with a human being? Never figured it out. Still winging it. You can tell it's bad. I'm not even going to have this as a step. We're not going to do that as its own step. That's a stupid point to have a step. You know what to do. What happens when you subtract a negative? It adds, right? You're subtracting a negative. Two negatives make a positive. So 40 minus a negative 59 is the same as 40 plus 59. Okay, 40 and 59, 99th power. Ugh. This is a perfect example of why I would not want to change everything back to decimals and, fix it from there on a test, because this is a 40-digit number. This is a 60-ish digit number that we'd be here all day, right? Just writing a bunch of zeros. So the entire purpose of scientific notation is dealing with numbers like these that you really don't want to deal with in decimal. And again, we need to fix our notation because we can't have 0 point something. We need 4 point something. We need to have our first digit that matters as the first one. So this guy's going to go 1 to the right. And remember, if it's moving 1 to the right, we subtract 1. So we end up with 4.6875 times 10 to the 98th power. Good. After those first 4, this thing's going to have 94 more zeros. That's a big freaking number. That's why we use this. We don't want to write that down. That's literally it. We have a use for this number is too big and I don't want to write it. That's entirely scientific notation. Let's do one more division. And then I'll let you guys have a break so your brains kind of come back to the world. Because this is going to be the last problem of scientific notation I do. Yeah. And we're happy about that one. So we have 6.1 times 10 to the 5th. Actually, you know what? I'm going to straight up write it as division right away because, like I said last time, you'll usually see them as division. So I'm going to do it that way. So we're dividing it by 1.2 times 10 to the negative 3. You know what? I don't like that that's a negative 3. It reminds me too much of the last problem. We already have had a negative power on the bottom. Let's make it a positive 3. That's a cheap fix. I just put a plus on it. That's a cheap fix. Okay, so you have a problem like this. You're on the test. You're like, oh God, this is ugly looking. Oh God. Well, what are we going to do? Just do the numbers on their own. Same as multiplication, same as the last problem. You're just doing the work with the numbers on their own. We have 6.1 divided by 1.2. We get 5.08. That 3 just goes on forever, doesn't it? Yep, sure does. Well, that's a tricky thing. What do I do with a repeating number on scientific notation? I've never done that before. Whatever, put a bar over it. It means it repeats. Good enough. If I was doing this in the real world on an engineering problem or something, that's what I'd do. That would work. Okay, and then I have to do this. So it's times 10 to a power, right? Well, again, just like the last one, if I have division with exponents, we just subtract the top power, the bottom power away from the top power. So top one minus the bottom one. Or you could think of it kind of when I did the lessons on exponents, I kind of taught them like canceling. I got 5 tenths here, I got 3 tenths here. You could cancel them that way, that's fine. So 5 minus 3 is what? 2. Yeah, times 10 squared. And you know what's nice about this one? It's already in scientific notation properly. It's already got 1 digit point the rest of our stuff, times 10 to a power. Cool. It works. This is also something that you probably wouldn't actually do in scientific notation because this is literally just 508 with a repeating 3. Times 10 to the 2 is a very tiny number. Okay, so are we happy that scientific notation is over? That's all I got for you on scientific notation. I could make up some more if you want. I see, you know, again, I'm not good at you know, interpersonal interaction. So maybe the emotions I'm reading from your face are excitement that you want more. Look how easy that problem was. Look at that. Look at that. Compared to the last one, look at that. Look how much we wrote. This is learning it. This is applying it. That's how much you actually need to write. Okay, so I broke all your brains. So we're gonna have a different kind of break. We're gonna give it a 10. So we'll have it until 7:35. And then I will start teaching you something entirely different to break your brain a different way. It'll be fun. Okay, everybody ready for the next nightmare? Yeah, cool. Yeah, have fun with this. So we've already done exponents. We've done scientific notation. We're going to do some radicals and roots. Radicals is essentially that's the name of the symbol. So we're going to be taking roots of different numbers, and it's effectively the opposite operation of applying exponents. Whereas you are multiplying something by itself multiple times with an exponent. When it comes to roots or radicals, you are essentially saying, hey, what is that thing what multiplied by itself that many times is this number? So it's literally just the opposite. So you can actually undo a power with a radical, and you can undo a radical with a power. They're kind of like, when I say they're opposite, they're literally opposites. If you want me to hurt your brain, it's they're literally fractional exponents, but we're totally not doing that. I will leave that for some point in your future endeavors. So square root is the opposite of squares, cube roots are the opposite of perfect cubes, and the exact same concept scales up to anything. 90% of what you will do will either have a square root or a cube root. Very seldomly will you have anything higher, and if you do, I'm going to do them in such a way that it'll work for any power you ever have to deal with. So as an example, since we know 2 squared is 4, if you were asked the square root of 4, it would be 2. 3 squared is 9, so the square root of 9 is 3. The other way around on a cube, we know that 2 cubed is 8, so if you had the cube root of 8, that is 2. I'm actually going to show you a nice way of doing these, and it's going to go back to us doing factor trees. 90% of these problems I do with factor tree, the other 10% are easy enough that you can eyeball them. So this is kind of how you look at simplifying square roots. So to simplify a term containing a square root, you take out anything that's a perfect square. That is, you factor inside the radical in such a way like a factor tree. And if you have a square root, that means that anything you have two of will come out as its own kind of factor. And I'll show you how to deal with that. The initial couple are just dealing with perfect squares and perfect cubes, but I'll actually show you guys how to do it with any number, whether it's perfect or not. Doesn't matter. Let's see. So yeah, if you look at the bottom here, this is a worked out example. This is every step on one little line, so it's not bad. You can look at 4 as being a 2 squared. 2 squared being 2 times 2. So either way you look at that, there's 2 factors of 2. So the square root of that is just going to be 2. Anytime I have a power of 2 inside of a radical, and the radical is the square root, it's just going to come straight out. So it works out really nicely. Cube roots are kind of the same thing, except in the case of cube roots, instead of dealing with perfect squares, you're dealing with perfect cubes. Same concept otherwise. So you can think of it as now that the same way that perfect squares, anything that had 2 of it would come out. If you're doing cube roots, anything that you have 3 of will come out. So because 2 cubed is 8, if you have the cube root of 8, the cube root of 8 is the same as the cube root of 2 cubed. 8 is 2 cubed, right? Those kind of undo each other and you just end up with a 2. I'll show you a couple of different ways on the notes of looking at that. It'll make your life so much easier. So I also decided to have a slide on larger roots than a square or cube. Now, this particular slide is just assuming you don't have magical perfect numbers of anything, right? So what happens when you have something larger than a square root, larger than a cube root, etc.? What ends up happening is it just scales up. The exact same thing that I talked about before works with any power. If I have a square root, that means 2 of anything will come out. If I have a cube root, that means 3 of anything will come out. If I have a 4th root, that means 4 of everything will come out. 5th root, 5 of everything. 6th root, 6 of everything. 500th root, 500 of everything. And I'll show you how to make very nice sense of this with factor trees. So literally all the examples I have for roots and radicals are these. That's everything. And most of these are stupid quick. I even have a couple on multiplying them together. And that is such a simple concept that I didn't actually need to have a slide to show you how to do it. So these actually are not bad. Kind of like exponents, they have very simple rules. They look complicated. And if you get those rules down, you're gonna look like a wizard. So let's say I have the square root of 144. There's a couple of ways to do this. First of all, if you know that 144, you look at that and you're like, hey, isn't that the perfect square of 12? You can do that. You can look at this and say, oh yeah, that's 12 squared. Okay. So the square root of a square cancels out. You end up with 12. That's it. That's all you got to do. It's not too bad. Now, let's say that you didn't know that. Let's say that you looked at this and you were like, 144, what the heck is that? I don't know what that is. Okay, that's fine. There's a great, like I've done that 100 times and you have no idea. There's even perfect squares that sometimes you run across and you're like, I wouldn't have known that. I don't know what the perfect square of 21 is. So that's fine. Another way to do it, remember factor trees. You can just break these down as far as you want. So that's 2 and 72, 2 and 36. I'm just going to do 2s all the way down until I can't anymore. So the concept I'm about to explain to you guys works for literally any root. If I have a square root, now, first of all, I might not have explained it too nicely, but square roots kind of have what's called an index. Square roots are nice. They don't have to show it, but with, say, a cube root or a fourth root or a fifth root, just as an example, any other root you would have is just going to have that number right there. That's it. That's the difference. So if I had the fourth root, it would look like that with a 4 there. Whatever. And what that's telling me is that's how many of a factor I need to come out of this guy. So if I don't have one, if it doesn't have one, then it's implied to be a 2 because you just use square roots so often that you don't need to write anything special for it. So I look at this and I say, okay, this is a square root. What does that tell me? It tells me anything inside that's a perfect square comes out of it. How do I know that? Well, if I got my factor tree, what's a perfect square mean? It means the same thing multiplied by itself, right? So every time I have 2 of something, that's a perfect square. That's a perfect square. That's a perfect square. Bunch of perfect squares, right? Okay. Well, what do I do with that information? Anything you pull out is going to come out front of the radical. And if you pull out multiple things, it's all going to be multiplied, because what's happening here, in order to get that 144, what's happening with these numbers? They're all multiplying together. So if I'm pulling out squares, what's happening? Well, they're still multiplying together. We haven't messed with it that much. We're just, cleaning it up a little bit. Okay, so this 2 will come out as a 2. This 2 will come out as a 2. And this 3 will come out as a 3. If you have anything left, if there's anything else that you didn't circle, if there's another factor that didn't come out, you would have a square root here and whatever is left. I'm literally just going to write whatever is left. Since this is the first one, I want this. That's an S. That's not an F. I'm losing my mind. Whatever is left, right? So anything that's left after this would just stay inside the square root. Because, hey, if it doesn't come out, where is it? It's still in there, right? Okay. So all the stuff on the outside multiplies together. All the stuff on the inside multiplies together. We don't have anything inside, so we don't have a radical anymore. 2 times 2 is 4, times 3 is 12. And that's where that comes from. Because if I don't see that this is a perfect square right away, then I got to work to getting perfect squares, and it works out the same. Works out exactly the same. If you see that it's a perfect square, cool, do it. If you don't see it, you have no idea, do a factor tree. Anything you have 2 of will come out as 1 of that factor. And it's all just going to multiply together. That's it. Now, what happens if it's a cube root? What happens if it's a fourth root? What happens if it's a 50 root? Well, what did we do with a square root? We look for squares. What would you do with a cube root? You look for cubes. What would you do with a fourth root? You'd look for fourth powers. That's it. It would just scale up. That's what I mean by scaling up, is whatever this number is, whatever our index is, this is the, I'm going to literally write it over here, index of the radical. Whatever that index is how many of that factor you would have to pull out for it to work. That's it. Nothing more complicated than that. No special funky rules. This square root of 144 is almost everything we need to know about radicals. That's almost everything, right? What do you mean almost? Well, I don't have an example of a cube root or a fourth root or whatever up here yet, so it'll be nice to do some of them, right? And I'll show you a couple of fun tricks for dealing with making our factor trees easier to deal with. Okay, so let's look at the next one. So for number 2, we have the square root of 75. That's a great example. You know why? Because it's not a perfect square, right? Nothing squares out to 75, right? So we're going to go ahead and factor tree this. First thing I can see, it's 75. It's 3/4, right? Cool. So that's 3 times 25. We know what 25 is, right? It's 5 squared. That's 5 times 5. Okay, so what do I do? Well, this is a square root. So anything I have 2 of will come out as just one of that factor, because the square root of 5 squared is 5. But hey, that's not everything. We still have this 3 inside. What do we do with that? Well, whatever's left is just left. It didn't come out of the radical, so where is it? It's still there. It's still under there. We can't do anything with it. So the 5 came out, the 3 stayed in. Cool. Not the end of the world, right? Easier than scientific notation? Okay. I know I scrambled some brains with that, but you know, it had to be done. And if you want, on Essential Ed, there is a couple of lessons on scientific notation, goes over them in a couple of minutes. If you didn't understand it tonight, might be a good idea to take a look and see if you can make more sense of it. So let's say I'm simplifying the square root of 4,500. Oh God, this could take a while, right? Oh God, you always make them harder than they need to be. Well, not really. You know why? Because you can be cheap. If there are zeros at the end of this, I'm literally just going to change this to a 45 and a 100. Cool, I've already chopped off half of my work. And you know what? We don't have to break it all the way down to the prime factorization of something. If I see that 100, I can actually just knock that into a 10 times 10 and say, hey, that's a perfect square right there. I can get away with that. You can 100% get away with that. If you don't want to do it that way or you don't think about it, you can do 250, 225, 5, 5, and you end up with 2 5s and 2 2s, which is still 10 times 10. So it'll work out either way. 45, that one's 9 times 5. Well, heck, that's another perfect square. That's 3 times 3. So we actually have a perfect square of 3 and a perfect square of 10. So what do we do with this information? Well, the 3 comes out, right? And the 10 comes out. And remember, whatever comes out multiplies together. What didn't come out? That 5. So where is it? It didn't come out, so it's still in there. Okay. We don't have any more math to do with that square root. All we really have is clean it up. 3 times 10 is 30. Cool. And I just thought of something that is not part of our examples. Okay. Let's see how I want to do this. So number 4, a little bit more complicated. We have the square root of 24 and the square root of 6 next to each other. That implies these two things are multiplying together. Now, oh God, what do we do? What do we do? Well, just kind of put them together. Because think about it. If these square roots, if we had, say, let's work backwards on number 3. Let's look at number 3. And we could think, hey, what was this? This was the square root of 9. This was the square root of 100, right? This could have been written. This could have been written as the square root of 9, the square root of 100, and the square root of 5. In fact, if you look at a math book that's trying to teach you how to break down roots, that's how they would write it. I hate writing it like that. That's stupid. Because 90% of the time, I know I say that a lot, every single time I've looked at a math book, it's always says, oh, just pull out the perfect squares as separate radicals. How do I know that? How do I look at 4,500 and say, oh, there's a perfect square of 9, there's a perfect square of 10, or 9 and 100, and how do I do that? I can't do that. I don't care how good you are at math, you can't do that. So factor tree is easier. I hate that. So what does this imply? Based on these two pieces of information, I could break this down that way. So if I was going the other direction, you can actually just multiply the stuff inside together. Multiply it together. That's it. Now, am I going to pull out a calculator and figure out what 24 times 6 is? Nah. Because we are breaking this thing down. And if we're breaking this thing down, we already know that whatever these two things multiplied together is, two of their factors are 24 and 6. So I'm just gonna factor them. We can actually just leave this alone and consider this one big ugly number. It's cheap, but it works. Because look at 24. What's 24? That thing's 4 times 6, right? Well, cool. That's a perfect square right there. Was that cheap? You betcha. Are you going to see that in a math book? No. But can you do it? Every time it'll work. Every time it'll work. So we're going to do it that way. That 4 breaks down to 2 times 2. There we go. We could pull out a 2. So we could pull out a 2, we could pull out a 6. We just have 2 times 6. 144. Oh, it was originally 144. That's that. Ignore Ben. Ignore Ben. I'm getting ahead of myself with what I wanted to say immediately afterwards. Ignore Ben. Ben's an idiot. Ben doesn't know how to speak. 2 times 6 is 12. What I meant to say is that if I had multiplied those two numbers together, we would recognize it as our first problem. It would have been 144. What I wanted to demonstrate with this example is that 1, a square root times a square root means that the stuff inside can multiply together. And 2, the other thing I wanted to drive home is the fact that since we are just breaking these numbers down, why am I going to bother multiplying them together if I'm going to break them down again? I mean, why? No reason. Do you have to do it that way? No, you can totally just multiply the numbers together, say it's a square root of 144 and be like, oh, I know that, that's 12. Cool, that's fine. It works. It works perfectly well. Now, I noticed that I don't have an example like this, so I just want to show you guys another example. Now, this is literally just going to be for the concept, so unlike what I usually do, where I make something giant and horrifying, I'm going to make it nice. Let's say I had 2 root 3 multiplied by, I don't care, 5 root 7, something like that. Let's say we had to deal with that. What do? Well, when you're multiplying things like that, what you end up doing is you just multiply the stuff outside together. So 2 times 5 is 10. And then separately, for the stuff inside the radical, you multiply that stuff together. 3 and 7, 3 times 7 is 21. I intentionally pick things that wouldn't break down any further just so we can have this in our notes. That is a useful concept. If you have 2 kind of complex radicals where you have something outside of the radical and something inside multiplied by another thing like that, the stuff outside multiplies together, the stuff inside multiplies together. If you only have something on the outside of one and not on the other one, Just put a 1 out front and think that you're multiplying that number by 1. Works out the same. Stuff outside multiplies together, stuff inside multiplies together. Now, as a completely out of left field example, if you had two radicals where one was a square root and one was a cube root, and you were multiplying them together, and you would say, hey, how would I do this? You just get decimals for both and multiply those numbers together. You wouldn't have a fancy way of doing that. At least until you learn something giant and horrifying that I don't want to tell you about. It can be done. It deals with common denominators, but I don't think you guys want to see fractional exponents yet. Because straight up, this thing is literally 27 to the 1/3. Don't worry about that. But an interesting thing to note is that my $150 graphing calculator that I got in like 2006 or something like that, I can't input something like a cube root, and it makes me horribly angry. So what do I do every time? I convert to fractional exponents and I punch it in my calculator. Literally every time, and it's annoying, and there's no good way of doing it. It's annoying. But this is literally, radicals undo things, because if I multiplied 3 by 1/3, it would be 1. So if I cube this thing out, it would just cancel that out, and that's where it comes from. So cube root of 27. A nice way to write it is recognizing, hey, 27 is 3 squared, or 3 cubed, right? 3 cubed. Cool. Awesome. The cube root of a cubed number is just the number. That's it. Kind of like the first one we did. If you can recognize that, hey, if we're doing a square root of a perfect square, it'll just come out. You're doing a cube root of a perfect cube, it'll just come out. If you don't see it, if you're, you haven't done this way too much, and you need to understand, hey, I don't really fully get this. Okay, that's fine. Cube root of 27. Okay, here's another way to do it. Factor tree. Same thing we did on the other problems. Exactly the same time. But we have a cube, which means I'm not doing perfect squares. Every time I have 3 of something, it'll come out. That's the difference with cubes. You're looking for 3 of a factor. Square root, cool. You're looking for 2 of the factor. Cube root, cool. You're looking for 3 of the factor. That's the difference. If there was a 4 right here, I would be looking for 4 of that factor. That's it. So by doing it this way, it actually cuts out so much weird stuff out of every math book I've ever seen, because they explain them in so many archaic, horrible ways that it legitimately has made me angry in the past. You can tell that like I get angry about this stuff, right? And it's like, if I just teach it this way, it works for all of them. All of them, every single one. There is not a problem that will not work for. Yeah, this is a perfect example. Cube root of 108. Is that a perfect cube? I don't know off the top of my head. Probably not, right? So what are we going to do? Same thing that we always do. Factor tree that guy. Break it down. This is 2 times 54, which is 2 times 27. Hey, 27, I recognize that. Which is 3 times 9, which is 3 times 3. Cool. We got 2 2s and 3 3s. I don't care about the 2 2s though, because this is a cube root. Do I have 3 2s? No. What do I have 3 of? 3. Kind of got like a weird lima bean thing going on there, but whatever. It works. So just like those earlier problems, whatever we have 3 of will come out as 1 of that guy. But what about the rest of it? Well, this is the first example where we'd had more than one thing stuck in there, right? We have 2 2s left. So what do we do with those? We just have 2 times 2 on the inside. Whatever didn't come out is still in there. So all you can really do is multiply them together and call it good. That's it. That's as tough as they're really going to get. I mean, until we start having complex ones with letters and fractions. Which I'm not gonna do to you. We're gonna try to streamline the rest of the class. So we're gonna make sure that Ben's crazy, stupid ideas of problems don't come out anymore. Speaking of, here's the cube root of 125,000. Cool, right? First thing you do on a problem like this, separate it out. It's 125,000. This is 125 times 1,000. Cool. Broke that down quick, right? Now, if you're good with powers of 10s, you could probably start chopping that down. I don't want to chop it into 2, right? We can already tell 1,000, that's 10 hundredths. Do I want to factor this even further? Not really, because if I can tell that I'm going to end up with a bunch of 10s off of that, and I'm in a cube root, I'm going to leave it like that. Now, if I was in a higher power and I had a bunch of these, you know, like 10s everywhere, I might consider chopping them into 2s and 5s because maybe the other part of my factor tree is going to have some 2s and 5s that go with them. But in this case, that's not happening. 125, that's 5 times 25, and 25 is 5 times 5. Well, heck, we have the same thing happen there. Those were both perfect cubes. So what happens? The 5 comes out, the 10 comes out. My brain is exploding. There we go. Nothing's left inside, so we're good. If I cubed 50, it would be 125,000. Would I have been able to tell that this is the perfect cube of 50? God, no. And that's exactly what a math book would tell you to do. Oh, just recognize that this is the perfect cube of 50. No, no, that's stupid. Nobody's going to know that. That's why I use factor trees. I started using factor trees while tutoring, and suddenly everybody managed to pull off all their homework. These ones are kind of squeezed close together in how I have it written, but they are separate guys, and you can almost tell the answer already, right? I have cube root of 2 multiplied onto the cube root of 4. Does this thing keep going out of focus? Why is that happening? All right. So I have the cube root of 2 multiplied by the cube root of 4. Okay. Just like the square roots, if I'm multiplying 2 radicals together, they have the same numbers, they have the same indexes, right? Index is 3, index is 3. That means they're going to just, whatever's on the inside is going to multiply together. 2 times 4, what is that? 8. Now, if you've done way too many math problems, you might be able to recognize, hey, 8 is 2 cubed. If you can see that, cool. The answer's 2. Awesome. If you can't, same thing happens. You would break things down. You would circle the thing you have 3 of, and it would come out. Worst case scenario, you would do that. Best case scenario, if you recognize it, you do that. Either way, doesn't matter, you get 2. You can do it that way, you can do it that way, either way. Whatever. Now, one thing, apparently I just kept forgetting to mention things on the slides for this guy. But I want to show you guys an example, couple examples of things that can happen and can't happen. And again, it's something that's addressed in a very weird way in math books, and I hate it, and it's so much easier. If you look at it this way, square root of, say, -4. What the hell, right? Well, here's the thing. Square root of -4 doesn't exist. There is no number out there where if I square it, I end up with a negative, right? Because think about it. Positive times a positive is positive. Negative times a negative is positive. Positive times a negative, that's the only one that's negative. So how could I have a perfect square that's negative? You can't. You get something like this where it's a square root of a negative number. Just straight up already, the answer, oh my God, am I running out of ink already? Does not exist. That's it. Does not exist. In the future, if you take, say, college algebra, they will explain to you that these are literally the definition of imaginary numbers. We've already looked at the real number system. There's also the things that aren't real. That's not real. That's it. That's it for imaginary numbers. That's literally the definition. Square root of -1. That doesn't exist. Cool. That's the basis for imaginary numbers. That's it. Cool. But what if I had a -8 inside, but it was a cube root? Can I have a cube of something that will end up with negative? Well, think about it. If I have negative times a negative times a negative, what do I got? Negative times a negative is a positive, but we got one more negative right there. It ends up negative because I'm multiplying 3 of them together. 2 of them cancel each other out and become positive. That last one always ends up flipping it right back to negative. So I know this is a weird way of writing it. Probably would make more sense if I had like x's there. -x times -x times -x is -x cubed. So what ends up happening is we can see something that starts developing as a rule, because we can do square roots and we figure out it doesn't exist. We can do cube roots and figure out it does. If I keep going, if I do 4th roots, if there were 4 of these, if I had one more negative right here, it would flip it back to positive, right? It would break. So what ends up happening is if the index of the radical is even, a negative inside, specifically inside, doesn't matter if one's outside, that just means you have a negative number. DNE does not exist. If the index of the radical is odd. Why did I write odd? See, I told you my brain is turning to goo right now. Is that some form of dyslexia that I'm just kind of like tripping on the edge of? Odd. If it's odd, a negative can, quote, come out. You can straight up take that negative on the inside and bring it outside. That will work every single time. How likely are you to see this on the test? I actually don't know how complicated the roots get on the test, but I can't imagine they are any more complicated than these ones at all, right? Not going to happen. So how do we feel? We feeling good? Let's look at my high set book and see how complicated roots get in this guy. Yeah, has been a while since I wrote it down. Hi, high set book. This is not really in here. I hate this book. I hate this. I hate the table of contents in this book, I guess I should say. I know it's in here. I just don't know where. Not there. Not there. Not there. I think the math workbooks that actually go to this book have square roots on like the first page. Kind of part of what you should quote unquote know. And I don't like that. That's not a good way of teaching math. How am I going to teach you, show you guys a radical without explaining what the heck it means? Ugh. You want to see something scary? The first time it actually shows a radical as part of a lesson is the quadratic formula. Yeah, this is literally something there is a problem in the practice test that you will see in the last week that I will show you guys. This is a formula that when you get to this point in math, you will use this so often. Negative b plus or minus square root b squared minus 4ac over 2a. You will use that so often that you will memorize it. But that is when you hit these points where you not only go past lines, you end up in things that are called parabolas, where they're kind of U-shaped. And yeah, your first introduction of that is totally going to be the last week of this class when I explain. Yeah, seriously, look how stupid this book is. Several pages later, simplify the square root of 24. Why? Why is this after that? Why would anybody do that to you guys? This book is stupid and it makes me angry. Yeah, literally the only thing I didn't really cover about this stuff is what I showed you multiplication. What about addition? Well, you kind of treat them as those both have square root of 2, so you just do the stuff outside. 4 square root 2 and minus 2 square root 2. What's 4 minus 2? 2 square root 2. I hate how they write this, by the way. It's so complicated looking, and it's not. You just look at the things that have like square roots, and you say, okay, I'm going to add the stuff out front of them. 3 square root 3 plus a square root of 3. Well, I got 3 of them plus 1 of them. I get 4 of them. What the hell is going on down here? Why do they explain these things like this? This is why I want to write a math book. This is stupid. Yeah, something like this. If you are on the high set exam or the GED exam and you see something like this and you're like, what the hell do I do with that? Right? Easy. Treat them each as their own separate problem. We just figured out how to break that down, right? We could break that down. We could break that down. We could break that down. You break them all down separately, blah, 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 blah. You get that. Cool. If they all have square root of 3s, you just add the stuff out front. That's it. What the hell? Why do they explain it that way? Literally all you do, break it down, break it down, break it down. If they go together, cool. If they don't go together, cool. Write them next to each other. Nobody cares. The ones that go together, go together. The ones that don't, don't.
Oh, okay.
Was that?
No, I didn't see the negative or the 9.
That thing?
Yeah, I didn't see that.
What
Is it 24?
Yeah, because, yeah, there's a negative on it. Yeah, you're literally just doing 8 minus 9 plus 25. So you treat them all as separate problems, you break them all down, and then if they have the same radical on them, you add the stuff in front. That's it. That is all of that. So I didn't even do any of that. Is that the end of the world? Yeah, because that's it. As long as you guys can break these down, if you can do this guy right here, then if you see something like this on a test, just think, okay, what can I do? What can you do there? I don't know, but I can break them down a little bit. Cool, try it, see what happens. You know what's gonna happen? You're gonna fall into the answer. Literally, that's it. You're just gonna fall straight into the answer. So if you're on a test, you don't know what to do, just look at the problem and be like, what can I do with that? What can I get away with on that?
Do you know how many questions are in the test?
I have no idea. I know that the practice test in the back of this book is 50 problems. Well, it was 50 problems. At one point, they removed something from trigonometry on here. And they just straight up deleted the problem. So the practice test in this book is 49 problems. And that's what we're going to do at the end of the class in a couple of weeks, is we're just going to cover that. And I'll show you how to do things like that. Look at this thing. Isn't that fun looking? Isn't that fun looking? Well, here's the thing. Here's another random little lesson here. It doesn't need its own page. I don't even care. Hey, what happens if I have the square root of 2 and I square it? That stuff just cancels, right? I have a square root and a square, it just cancels. That's it. So why did I not save my place? Oh, Ben, you jackass. So if you're on a test and you see something like this and you're like, oh God, I haven't done that. He did one of these on the practice test. There's literally one of these in the practice test in the back. How do I solve that? Well, you get the square root alone. Don't worry about the crap inside. You add the 6 over. Okay, that's what they do first. They add the 6 over. Wait, how you cancel a square root? You just, oh God, they didn't even show it. I hate you guys. They wrote it, square both sides. That's it. How do you get rid of that? You square it. You put a little 2 up top, you put a little 2 up top over here, you square both sides. You get the stuff inside is equal to 144. What do you do from there? Just whittle it down until you get the x alone. Subtract the 9 off, divide off the 5, you're done. That's it. It's not the end of the world. It's weird looking at first. You haven't done these. Usually you go over them in a math class for an entire week. I just told you all of it. There's nothing special. There is literally nothing special to them. Yeah, there's even a check. Worst case scenario, you do a problem like this, you're like, oh God, did I screw that up? Do I have enough time to check it? I don't know. Throw it back in there, see what happens. Why would you write the solution is not extraneous? Shut up, guys. If you get the same thing equals the same thing, your check worked out. Yeah, look at this weird problem. Oh God, what do we do? Add the 1 over and square both sides. That's it. How do you get rid of a square root? You square it. That's it. Are they weirder looking than that? You remember the distributive property? This is literally just square root of 3 times both of those. That's it. We just figured out how to do multiplication on those, right? You just multiply the stuff inside together. If there's stuff outside together, you multiply that together. Cool. All right. That's all you're going to do here. That times that, and then that times that. Cool. I'll show you how to deal with those too. Those are freaking easy. Yeah, I can't make it any more complicated than that. That's literally as complicated as those get. Do we have any questions? You're like, what the hell, Ben? You just went over all this stuff that you didn't even actually show me anything written. Yeah. But don't worry. We haven't gotten to that point yet, but we're gonna. This is all gonna be stuff I do in the last week. So I don't really want to do any more math, neither do you. So we're gonna call it good. We're gonna pick up in the next class. We might do a little bit of review. I might throw in a couple of those random radical problems just for funsies. Then we'll jump into measurement, units of measurement. It's great. You're doing unit conversions. It's literally feet to miles and blah, 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 blah. My literal least favorite one is cups, ounces, pints, quarts, gallons. That's the stupidest freaking system ever. Hey, you want to know something really terrifying? If you convert prices of gas in London right now to US dollars and they do it by liters, so you multiply it by 4, they're actually paying about $8 a gallon over there.
Really?
Yeah, we have no problem at all compared to the rest of the world. Our gas prices worldwide are cheap. Isn't that horrifying? This is why I have a bicycle.
All right, I'll see you Thursday.
Yep, have a good night, everybody.